is the same as the force between two current carrying wires.
All right, so let's do a quick review. All right, so the current carrying wires will either be attracted or repelled by each other, right? So the question becomes why. That'll require a fast little review, and then we need to build on that material. All right, so Ørsted discovers that the current causes magnetism.
Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current.
So what that means is the magnetic field is going to wrap itself around the current wire. If there's current, there's going to be a circulating magnetic field around it. We kind of know how to figure out the direction of the magnetic field by using a compass, or obviously instead of using a compass, once you figure out the direction that the magnetic field is pointing, you can also figure it out using the right hand rule. All right, so you line up your thumb in the direction of the current, and the fingers will curl in the direction of the magnetic field. So far, so good. Everything that we're discussing so far is conceptual physics, except now we have to express the same idea mathematically. All right, there are two ways of doing it. One is called the Biot-Savart's law. All right, so that's something that we will touch on in about half hour. And this stuff is somewhat involved, so that's going to require a little bit of calculus. So Ørsted discovers that the current causes magnetism, but how do you express the strength of that magnetic field? And then you do the work, and then blah, blah, blah. Eventually, you come up with a formula that looks like this. All right, so this formula is going to give us the strength of the magnetic field at a certain radial distance away from the current wire. All right, so that's the formula that we're going to focus on before worrying about the derivations.
Is the same as the force between two current carrying wires.
All right, so the application of this formula is that
is the same as the force between two current carrying wires.
All right, so the wires will be attracted to each other if the currents are moving in the same direction, or they will be repelled by each other if the currents are moving in opposite directions. Currents are in the same direction, there's going to be attraction. Currents moving in opposite directions, there's going to be a repulsion. So the question is, what's causing the attraction and what's causing the repulsion of these wires? Attraction and repulsion is caused by the magnetic force. All right, so this current is going to cause a circulating magnetic field around it. Notice that the second current wire is within the influence of the magnetic field generated by the first current wire, right? So the current is going this way using the right-hand rule number two. Using the right-hand rule number two, you can figure out the direction of the magnetic field. You know the magnetic field due to this current is going to be moving in the opposite direction right at that point. Also, the current is moving in this direction, the magnetic field is in the opposite direction. So this time, using right-hand rule number one, you will notice that this wire is going to experience a force to the left towards the first one. The same thing is going to happen to the first wire. So the magnetic force that it's going to experience is going to be directed towards the second one. All right, if the currents are moving in opposite directions, this time the magnetic force is going to cause a deflection. All right, so mathematically, it's the same thing. All right, so here's the magnetic field due to the first current element of the current wire. All right, so this is the Biot-Savart's. We end up getting this from the Biot-Savart's law, whatever that is, you will find out shortly. So this is the formula for the strength of the magnetic field at a certain radial distance away from the wire. All right, so separation distance between the wires is going to be R. So this is the strength of the magnetic field at a radial distance R away from the first wire that you're looking at. Current is coming out of the page, the magnetic field acting out in 90 degrees. So you line up your thumb in the direction of the current, which is coming out of the page. Fingers are lined up in the direction of the magnetic field. Your palm is going to point to the right. So that's the magnetic force that's going to be responsible for the deflection. All right, so the current coming out of the page, this is I2. So that's going to become I2 shortly. This is the length of this wire. This is the magnetic field due to the first current. And this angle is the angle between the magnetic field and the direction of the current. In this case, it's going to be 90 degrees. So this is the magnetic field due to the first current element that we're looking at. All right, so B becomes the strength of the magnetic field. This is the magnetic field generated by the current. And then you kind of tidy it up a little bit. And so this becomes the force acting on this magnetic force, acting on the second. This is the magnetic force acting on the second wire due to the magnetic field generated by the first wire. That's it, straightforward. Okay, so a bunch of formulas. All right, let's focus on the formulas first, and then we'll focus on the derivation. There are 4 formulas that you need to know inside out. All of them are on your formula sheet. If you see this formula, this is going to give you the strength of the magnetic field at a certain radial distance away from a wire. That's it. So the further away you're from the wire, the weaker the magnetic field is going to become. That's it. If you have a circular loop, current loop just like that, so here's what the magnetic field does around the loop. You're going to be interested in the strength of the magnetic field right at the center. So what is the strength of the magnetic field right at the center? The strength of the magnetic field is like this formula, except it's going to have pi missing. All right, so if that's got pi, looking at the strength of the magnetic field of a straight wire, radial distance away from the wire. The pi is missing, which means that you're dealing with a circular loop, and you're looking at the strength of the magnetic field right at the center of the wire, right at the center of the loop. Instead of a single loop, you can have multiple loops. All right, so when you put multiple loops together, it's known as a solenoid. So you have a coil of wire in this case. This is going to have a length. This is lowercase l represents the length of the coil. And it's got number of turns. Capital N represents the number of turns that it got. L is the length. Capital N is the number of turns. In every single loop, the current is going to be moving in the same direction, generating a magnetic field pointing in the same direction in essence. All right, so the formula that you're looking at, which is this, is going to give you the strength of the magnetic field inside the coil that you're looking at. All right, so notice that you got capital N here. All of a sudden, the capital N kind of magically turns to lowercase n. They don't mean the same thing. This lowercase n represents the number of turns per unit length, number of turns per length. That's what you're looking at. All right, so this is going to represent the number of turns that you have within a certain length of the wire. All right, so instead of calling this a coil, the technical term is just solenoid. So this setup is known as a solenoid. All right, guys, I got news for you. This is not an engineering course. It's a physics course. And the physics courses, and likewise in the engineering courses, you will do the same thing. You cannot be doing formula hunting. These become the main formulas that you will get to use in problem solving. But at this point, it's not high school. The question becomes, how do you come up with these formulas? You don't get these formulas from space aliens. We derive these formulas based on geometry. You have a pi here, you have a pi there, and why does the pi vanish? All right, so those are the things that we will focus on. So the derivations will become important at this point, because this is the sort of stuff that you will be building upon when you guys start taking engineering level courses. All right, so here's your solenoid. This is your coil. A couple of things about this is interesting. All right, we'll do the derivation later. I'm not worried about the derivation. Something that we need to emphasize here, it's not the derivation, evidently I'm after. This formula that you're looking at is going to give you the strength of the magnetic field inside a solenoid. It gives you the strength of the magnetic field on the inside. If you're looking at it, notice that the spacing between the lines are even. So the lines are evenly spaced. So what that means is the strength of the magnetic field inside is going to be constant. All right, so whenever somebody did the derivation or does a derivation in this case like that, we're only interested in the strength of the magnetic field on the inside. And the underlying assumption is it's going to be constant within the solenoid. That's what it means. Also, there's an underlying assumption. The second assumption is this is an infinitely long solenoid. So the length is infinite, which means that whatever the magnetic field on the inside is never going to be able to escape from it. All right, so these are like simplifying assumptions. Accuracy of your results in physics always based upon the accuracy of your assumptions. If your assumptions are bad, the solution is going to be bad. Here, it's an oversimplification because we're always interested in the strength of the magnetic field inside a solenoid, and then strength of the magnetic field inside a solenoid. When we are talking about it, we're only interested in the strength of the magnetic field towards the middle of it somewhere. All right, so that's what assumption here is. The strength of the magnetic field is going to be constant for application reasons. So here's your solenoid. The current is going to be going in that direction, and you can figure out the direction of the magnetic field by using the right-hand rule. All right. Now the reality, the formula that I gave you only represents this reality that I mentioned right in this section. All right, so in a very small section inside the solenoid, the strength of the magnetic field is going to be constant. So that formula is only applicable within this region. Notice that towards the edges, strength of the magnetic field is no longer constant. Notice that the lines are diverging away from each other. So understand your assumption. If you take a solenoid and then turn it into a donut, it turns into your toroid at that point. All right, so when it turns into a toroid, there are a couple of things that we need to focus on. Number one, what happens to the strength of the magnetic field inside the toroid? All right, so these green lines represent the strength of the magnetic field. All right, so do you think the strength of the magnetic field for the inner line, do you think it's going to be the same as the strength of the magnetic field for the outer line? Okay, so speaking of a toroid, let me check to see if we have a better picture of it. The current is coming out of the page here, and then it's going into the page. Current is coming out of the page, it's going into the page, coming out of the page, and it's going into the page. All right, so that's your toroid. All right, so toroid is a donut-shaped solenoid, in essence. And notice that the magnetic field is going to be trapped within it. And obviously, what's generating the magnetic field is the current loop inside of it. All right, so once again, the strength of the magnetic field for the toroid is going to be exactly the same equation. Let's just back out of this. All right, so the strength of the magnetic field inside the toroid is going to be exactly the same as the strength of the magnetic field inside the solenoid. All right, so they look exactly the same. So the question becomes: does this mean that the strength of the magnetic field also constant inside a toroid? All right, so the strength of the magnetic field inside a toroid, is it also constant? All right, does this mean that the strength of the magnetic field of this line is the same as the strength of the magnetic field of an outer line? All right, so that becomes the question. So this is R1, the first magnetic field is located here. This is R2, this is the location of the second magnetic field. All right, now you have to look at the meaning of this lowercase n. The lowercase n is the number of turns per unit length. All right, so this is the number of turns per unit length, but what is the length of this toroid? The length of this toroid is going to be the circumference of the toroid. So it's going to be 2 pi r. All right, so which means that we have to do a back substitution into that one. And when you do a back substitution into lowercase n, you will notice that the strength of the magnetic field is going to have a radial dependence. All right, so you got this inverse relationship. In essence, if you increase the distance with respect to the center of a circle, all right, the strength of the magnetic field is going to diminish. This goes up, B is going to go down. That's what it means. So which means that the strength of the magnetic field at the inner radius is going to be actually stronger than the magnetic field in the outer radius. All right, so that becomes the meaning of it. So strength of the magnetic field is going to have a radial dependence. All right, so which means that this magnetic field is going to be stronger than the other one. Okay, guys, what I'm doing is a bit of a trick because sometimes my teaching style is untraditional. I posted a Yale lecture because I love the guy. He's like one of the best lecturers as far as I'm concerned, except his style is very traditional. It's very mathematical. That's the style that I'm used to. That's not the style that I use because not much learning usually takes place. You lecture, the whole idea of the lecture is to give lecture notes, and not much understanding usually takes place if everything is that mathematical. All right, so I'm using the same method as Yale right now. I just said, hey, listen, what's the strength of the magnetic field? Does the strength of the magnetic field inside the toroid, does it change? Why does it matter? It does matter, as you will find out when you start taking your engineering classes. All right, because this is not conceptual physics. This is real physics, got real applications. So I need to know whether or not the strength of the magnetic field here is going to be the same as that. That becomes important. And then we do a little bit of a mathematical finagling. You just move the math this way and that way. All of a sudden you realize that, hey, there's an inverse relationship. And then mathematically you're done. All of a sudden you realize that the strength of the magnetic field within the inner radius is going to be stronger than the strength of the magnetic field in the outer radius. So the next question becomes, why? That becomes your conceptual test question. So the question, can you figure that out? All right, so now you have to do a little bit of thinking. Why? You cannot provide a mathematical explanation. As soon as you try to do a mathematical explanation on the test, if you're lucky, you'll get a half a point for that. Mathematics just describes what happens. It doesn't really explain it. Now you have to start thinking about it. Why is it that the strength of the magnetic field, it's got a radial dependence? All right, so what's happening with that? So what you need to do is now you have to look at the spacing between the wires in the inner radius versus the outer radius. Okay, remember the number of lines per unit length and the number of lines per unit length. And all of a sudden notice that the spacing starts to increase and you get to the outer lines. And then obviously it's going to cause a variation within the strength of the magnetic field on the inside. So you have to kind of think about it and figure it out on your own. Guys, this is going to be, what I'm saying is this is going to be one of your test questions. You cannot Google this sort of stuff because the understanding cannot be Googled. This is something that you have to kind of figure out. All right, so I'm just giving you a hint. This is a test question. All right, you guys usually get tested on understanding, not necessarily knowledge. Knowledge is, it's not, this knowledge is high school. Yeah. All right, the knowledge is, here's the formula, boom, 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 here's the meaning of it. That's it. So the question is, why is that happening? Now that's real physics. Also, you get tested on your mathematical understanding of what's going on. All right, so having said that, to get a single loop, a wire. So the strength of the magnetic field in the metal is going to be found using a certain equation. And this is the equation I said that we will get to use. So the question is, how do we come up with that equation? So that's going to be the next part of the discussion. All right, so we got the same wire. The current is moving in the opposite direction. And then it makes a loop and then keeps moving in the opposite direction. All right, so the question is, what is the strength of the magnetic field in the metal? All right, so that becomes a question. It looks like it's a simple enough problem. It is a simple enough problem, but requires pretty good understanding of what's going on. All right, so what you need to notice is, here's a straight wire. Due to the straight wire, the magnetic field is going to be going into the page right at the center, so it represents the center. And due to the loop, there's going to be a contribution of the magnetic field, which is also going to be coming out of the page. So there are two magnetic field components that we have to worry about here. So if that's the case, what is the net or total magnetic field within this loop? That's what we're going to focus on. So there's a current wire, the current is moving in the upward direction, and then boom, it makes this loop. It looks like it's kind of close, but it's not. There's going to be a very small gap right in the middle. Boom. And then we're going to be interested in the strength the magnetic field right at the center. So we're, oh. All right, so due to the straight wire, the magnetic field is going to be going into the page at that point. And due to the loop, the magnetic field is going to be coming out of the page. Due to the straight wire, it goes into the page, and due to the loop, it's going to be coming out of the page. All right, so magnetic field due to the straight wire, S is going to be straight wire. It goes into the page if you use the right-hand rule. And the magnetic field due to the loop is going to be coming out of the page. So this is, C represents the circle. All right, so if the magnetic field is coming out of the page, we'll take that to be positive. If it's going into the page, we'll take that to be negative. All right, so we will just write it to center. So we'll just put up the magnetic field contributions. All right, this one is coming out of the page, so it's going to be positive. This one is going into the page, so it's going to be negative. All right, at this point, we're learning to use the formulas. All right, so the magnetic field due to the circle or the loop is going to be mu naught times I divided by 2R. R is going to be the radius in this case. And the magnetic field due to the straight wire is going to be mu naught times I divided by 2 pi R. Once again, R is going to be the radius at that point. All right. Or in this case, this is going to be radial distance with respect to the wire. All right, so that's it. Factor out the like terms. And then if there are numbers, just plug in the numbers, especially if you're majoring in electrical engineering. And this is the fundamentals of physics. This is literally the alphabet of what you guys are going to be doing. All right, so just want to make sure that your understanding is there. Okay, so I want you guys to have a conceptual understanding as well as a mathematical understanding of what's going on. So the current is going to cause a circulating electric field. No, the current is going to cause a circulating magnetic field. So this formula is going to give us the magnitude of the circulating magnetic field at a radial distance away from the wire itself. All right, so Ørsted comes up with the discovery. And then here's the mathematical expression of what Ørsted is talking about. All right, so the current is I. Obviously, we understand that. Okay, I gotta just make sure that we have these ghostly images all over the place. Okay, so mu naught represents a constant. All right, so the only thing that you got pi is a constant, 2 is a number, obviously, mu naught is a constant. So I is the current and R is the radial distance. So the strength of the magnetic field is going to diminish with the radial distance. So it's going to diminish inversely. It's going to change inversely with the radial distance. What if you have a current loop? Well, this time the strength of the magnetic field is going to be found using this formula. The only difference between that formula and this formula is pi is missing. All right, so 2 questions. How do we come up with a formula like that? And how do we come up with a formula like this? Okay, so where do we get these formulas from? And then instead of a single loop, what if you have multiple loops? What if you have a coil and then this coil is called a solenoid? So here's the length of the coil. Here's the number of turns that you have. That makes up this coil. The current is going to be moving in the same direction in every single current element that you're looking at. So obviously there's going to be a circulating magnetic field. So what is the strength of the magnetic field within the solenoid? So the strength of the magnetic field inside is going to be given by this formula. Once again, it depends on the strength of the current. The stronger the current is, the stronger the magnetic field. On top of that, it depends on the number of turns per unit length that you have. So N is the number of turns, and lowercase l is going to represent the length, number of turns per unit length. So how do we come up with these formulas? That's what physics is all about. So in engineering, the emphasis is different. In physics, we deal with the nature itself. So how do we come up with these formulations? So the first formula is the first one that we will tackle. All right, so let's go back to the first one. All right, so Ørsted discovers that the current causes a circulating magnetic field, and this is the expression, mathematical expression, that's going to give the value of the circulating magnetic field at a radial distance r from it. All right, so there are 2 attempts at this one. All right, so the first attempt comes from Biot-Savart. All right, so mathematically, this is important. I want you guys to go through the complexity of it. And then there's an idealization or simplification of what Biot-Savart came up with by Ampere. Okay, Ampere solution is great. It works, it's fine, except it doesn't work 100% of the time. All right, so Biot-Savart's solution is going to work 100% of the time. So Biot-Savart's law is a way of tackling the strength of the magnetic field for any single current wire. I don't care if it's a straight wire or if it's a loop wire, it doesn't matter what it is. It's always going to give you the correct expression for the strength of the magnetic field. In this case, we got a wire, which is kind of a little bit looped, it's curved, the current is flowing in this direction. All right, and we're going to be looking at this segment portion of the wire that carries the current. And then we want to know how much of this segment of the wire, current carrying wire, is going to contribute to the magnetic field at a certain distance away. All right, so the magnetic field, due to this current element, is going to be pointing into the page. All right, so they came up with a mathematical expression, and it goes like this. All right, so obviously, this is the length of the wire. All right, so the length has a direction in this case. The direction is the same as the direction of the current. For whatever the reason, this length is being used as a vector for reasons that'll become fairly obvious in the future, obviously. All right, so you got this angle between this vector and that vector. You know that the vector, the magnetic field is going to be perpendicular to the area spanned by these two vectors. All right, so it's going to be perpendicular to the position vector. It's also going to be perpendicular to the current in the direction of that current that you're looking at. This vector expression, which is a combination of current and the length of the wire. All right, so which means that just from a mathematics perspective, forget physics, you can actually employ the cross product for that. All right, so this cross that is going to give you a vector. It's going to be pointing into the page in essence. And then what they do at this point gets kind of weird because this gets divided by r squared, similar to what Newton came up with, but Newton had a justification. So which means that the strength of the magnetic field is going to diminish as radial is the square of the distance. I'm not sure what the justification of it was, but this is what they came up with. On top of that, they decided to multiply everything with some kind of an adjustment constant. Adjustment constant in this case is going to be 10 to the minus 10, I think. All right, and then they multiplied that 10 to the minus 10 by 4 pi divided by 4 pi. And so they came up with an expression like this. All right, guys, this is known as a unit vector, which means that the cross product is taken relative to a unit vector. Unit vector is just that it's got a value of 1. It's just a direction vector in essence. It doesn't mean anything else. All right, so the formulation is just a trick. It's just a mathematical trick. All right, and everything gets multiplied by some kind of an adjustment constant. This is mu naught is 10 to the minus 12. Okay, I'm just thinking right now. It's 10 to the minus 12 is an adjustment constant. So 4 pi divided by 4 pi is going to make mu naught 4 pi times 10 to the minus 12. Okay, well, I got to check that. I'm saying 10 to the minus 12, but we'll find out. All right, so this is unit vector. Like I said, that can be expressed in terms of a vector divided by its magnitude. So this formula can be expressed in terms of that formula. And then we have mu naught. This is 10 to the minus 7. Okay, so I was thinking in terms of epsilon naught, that's going to be 10 to the minus 12. All right, so which means that this is mu naught, the strength of this expression, the strength of the magnetic field in essence is going to be 10 to the minus 7. So that's just an adjustment constant. Multiplied by 4 pi and divided by 4 pi gives you the expression that you're looking at. All right, so I'm trying to decipher, I'm trying to put myself in the shoes of these two, Buell and Savard, trying to figure out what they were thinking. So this is more of a mathematical modeling. So the only question that I have is how did they know that this strength of the magnetic field was going to diminish as the square of the distance? Coulomb, once again, made the same assumption. And Newton was the only one who was able to justify it. That later became the inverse square law. Okay, and Newton was at the time developing calculus in the background. All right. So this mu naught is known as the space permeability constant. What that means is evidently it's going to tell you how fast the magnetic field is going to travel in space. It's not going to travel at infinite speed. I can tell you that it's not going to be an instantaneous force either. All right, so which means that as soon as there's magnetic field, it's going to take time for it to go from point A to point B. So which means that the space is going to put the brakes on somehow. All right, so that's the implication of it. All right, so once again, the cross product is what we were using. This is a fast review, excuse me, what the meaning of a cross product is. A cross B is going to give you C. All right, so A and B will span this region, and C is going to be perpendicular to both of them. All right, so this is otherwise known as the right-hand rule. So line up your fingers along the direction of the area vector, and then you curl your fingers towards the second vector, vector B, and your thumb is going to point in the direction of C. It's going to give you the direction of C. All right, so this is the vector expression. This is the scalar expression of what you're dealing with. The sine of theta is going to be the angle between A and B. All right, so what that means is we can take this expression, a vector expression, and represent it in terms of a scalar expression. All right, and the vector expression can be expressed in terms of a scalar expression. Instead of using this one, now I'm using this one. All right, so it's going to be IDS, and you're looking at the cross product between a unit vector and S, the length vector. I'm going to say, I don't know what to call it at this point. And all of a sudden, obviously, R is going to disappear because it's a unit vector. The only thing which is going to survive is the sine of the angle. Denominator is going to be R squared, if you want to use that expression. All right, so denominator is a scalar expression. If you see it, this expression, that means you're interested in the magnitude of the vector in the denominator. So it's from calculus, in essence. All right, so that becomes this Biot-Savart's law. All right, so now that we got the Biot-Savart's law, I gotta get out of here. Okay. Okay, so there are two derivations involving this one. One of them is, the first one is going to give us the formulaic expression of the strength of the magnetic field inside a straight wire. The underlying assumption is this is an infinitely long wire. Okay, what if it's not infinitely long? Well, obviously it's going to give you some complications. All right, so it's an oversimplification. It's a simplifying assumption in order to get the math now. All right, so despite the fact that I'm not going to give you a problem regarding those sort of stuff on the test, you will have tons of problems next step up, because when you will have to take electromagnetic wave theory, the emphasis is going to be on the mathematics next time around. Because you will have an engineering professor, they will put the emphasis on mathematics. All right, not much discussion regarding physics will ever take place unless your instructor is a physicist. So this is your opportunity to actually learn physics and get really good at it. Better you're at physics, the easier the engineering is, believe it or not, because they will put everything on a math track at that point. All right, because physics is tough to comprehend, but math is easier to do. So it's easier to deal with mathematics, and then physics is going to get pushed to the background. I know that because I also teach engineering, and I was also doing my master's in engineering before working on PhD in physics. All right, so what's happening here? What's happening here is not that you got a straight wire just like that, infinitely long, and that we want to know the strength of the magnetic field at a certain radial distance away from the wire. Biosphard ended up doing us a favor. They came up with a mathematical expression which we know to be accurate. So we will apply this expression to any geometry you want. I don't care how you want to actually shape your wire. It's always going to give you the strength of the magnetic field at any radial distance that you want. All right, so the straight wire is the easiest one, so that's the one that we will get to use. All right, so what do we know? Position vector is going to locate the position where you're interested in the strength of the magnetic field. You know the magnetic field is pointing into the page at this point. The current is moving in the upward direction through this differential segment of the wire. So what I'm doing here is I'm going from a vector expression to a scalar expression for computational purposes. As soon as I do that, all of a sudden we got a slight problem. The problem is the angle. All right, so remember this angle is the angle between these two vectors. All right, so you got the differential length as a vector pointing in the opposite direction, and you got the position vector pointing towards this point where you're interested in the strength of the magnetic field. All right, so what do we do? All right, so which means that we have to follow the rules of mathematics. All right, the first thing we will get to do is set up the angle, which I am. So the angle is outside. Okay, so I wouldn't know what to do with an angle outside because, you know, this R is R. I don't know anything about the length of this wire. As far as I know, it's going to be infinitely long. So with angles, it's better to come up with something that you can relate to. Triangles are things that we can relate to. All right, so why not make a triangle? So you can measure the distance to this point from the wire. So call this R. All right, so this is the differential segment. Okay, so I can measure the length up to that point. All right, so I'll call that S. So that's going to be the segment that I'm interested in. I noticed that I made myself a tiny little triangle, except I still have a problem. The problem is this angle is outside. So it's, unless I can somehow express this angle somewhere within the triangle, I'm screwed. There's nothing I could do. All right, so at this point, the math comes to the rescue. All right, so what do I know? I know that this is 180 degrees, it's flat. And so this angle that you're looking at is going to be 180 degrees minus theta that you're looking at. 180 degrees in terms of radius is going to be pi, so it's going to be pi minus theta. That's it. All right, so I was able to move this angle into the triangle, but now somehow I need to come up with an expression for sine of theta. All right, at this point, it's trial and error. All right, it requires a bit of understanding of trig and hopefully some of the trig identities. That's all we have to do. All right, so what would happen if I were to look at the sine of this and check to see if sine of this expression would give us sine of theta? All right, so that's trial and error at this point. If you have the experience, obviously that's the way you would do it. If you don't have the experience, just trial and error. All right, so when you have an expression like that, this is a trig identity. So this could be written out just like that. So you got sine of theta times the sine of pi times the cosine of theta minus, now you have the cosine of theta, cosine of pi times sine of theta. All right, so if you employ this trig identity, let's check to see if this is going to give us sine of the angle. All right, so sine of theta, 180 degrees is going to be 0. Cosine of theta is going to be -1. So the first expression drops out. The second expression that you're looking at, negative times negative is going to be positive. So I'm going to get rid of that negative. All right, very good. So all of a sudden we have an expression for sine of theta, and that expression for sine of theta happens to be the same as this expression here. So boom, I'm able to move this angle into a triangle right there. Okay, now we can actually get some work done. All right, so the rest of it is measurable. So the sine of this angle that you're looking at, sine is going to be opposite of the hypotenuse. Opposite is this radial distance, and the hypotenuse is the magnitude of the position vector. That's what I'm trying to express. All right, now I'm visualizing for you. All right, so opposite of the hypotenuse is going to be that. All right, instead of using the hypotenuse as a vector, I'm using it as a magnitude, scalar expression, do a back substitution. All right, and all right, so this is r squared, this is r, so this is going to be r cubed, obviously. Okay, what else am I looking at? That's it. So you got the capital R, so keep it as is. All right, so ds is the differential length. All right, so this, all right, so r is going to change depending upon your length. So this is a variable. Capital R is not going to change. This is the radial distance, so it's going to remain the same. So ds is going to be it's going to be a function of r in essence. So we need to come up with an expression for that one, because we will have to take the integral from negative infinity to positive infinity. All right, so you got the, which is the same as going from 0 to infinity twice. Let's do a back substitution there. All right, there's a simple cancellation there, so let's take care of that. And then let's stop at this point. Okay. S goes from negative infinity to 0 to positive infinity. And notice that when you start to move this differential segment, when you start to look at the contribution of the current to the magnetic field here, 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 all the way up to infinity, notice that the R is going to keep changing, right? So, which means that the R is going to be a function of S. All right, so R is going to be a function of S. R is going to change with S. So obviously this is a triangle and this is the hypotenuse. So I just use the Pythagorean theorem to come up with an expression for R and do a back substitution in it. All right, and then this is going to be 3/2 because this is going to be the square root of whatever the expression is. All right, so at that point, how you do an integral like this, I don't care. Use calculus, use MATLAB. That's what you want to do. Use a calculator, look it up. You can do it any way you want. All right, this is as far as physics goes. When you're done with the integral, this should give you 1 over r squared, the radial distance to that point. And notice that you have r, you got r squared, so there's going to be a cancellation. And this becomes the final expression, which is the same as the expression that I had in the beginning of the lecture, which is this. So Biot-Savart's law, this is a simple application of it for an infinitely long straight wire. So that's how mathematics works out. And then this guy comes along, again, a Frenchman, and he has a much more elegant solution to this problem. And this is going to work most of the time, not 100% of the time. Biot-Savart's law is going to work 100% of the time. This works if you have a nice little shape. This is like the Gauss's law for current, and some that we can actually employ from time to time. All right, for example, the current is coming out of the page, right? I don't care that this is an infinitely long wire. This is going to work for any wire. And you got the circulating magnetic field in this fashion. So the question becomes, what is the strength of that circulating magnetic field? All right, obviously, we will have to come up with the Biot-Savart's law, the Biot-Savart's expression. All right, so the strength of the magnetic field around a current wire. All right. This is the wire itself. This is the thickness of the wire, capital R is going to be the thickness of the wire. What we'll have to do is we have to do an Amperian loop, which is going to be a radial distance away from the center of the wire. Now we know that the magnetic field is going to be circling around the wire in this direction, otherwise known as the right-hand rule number 2 from my perspective. All right, so Ampere came up with this mathematical expression. All right, this is a simplification of what this guy was thinking. This guy is like the French Gauss in a sense. All right, what he's saying is the circulating magnetic field. So this is B is the magnetic field, and it's just circulating in this direction. And if you see a small loop like that, it usually indicates that you're circulating it in the counterclockwise direction along this differential segment. All right, so ds is going to represent the path that it's going to take. All right, so you got 2 vectors. You got the magnetic field, and following the length of the Amperian loop in the counterclockwise direction. So what that means is the strength of the circulating magnetic field along the direction of this loop is going to depend on the current within the loop, and that current within the loop may not become some kind of a proportionality constant. So it's just going to give you how much the current is going to affect the value of the magnetic field at that radial distance. That's what it means. All right. So Ampere comes up with something real elegant in essence. Looks at it, it's just pulling a Gauss out of his butt, basically. He says, okay, just come up with a loop. Make sure that the loop is going in the counterclockwise direction. And let's check to see how much of the magnetic field is going to be along the direction of the loop, in essence. And the amount of magnetic field along the direction of the loop is going to depend on the net current within the Ampere loop. That's it. Remember, this is a vector product. Once again, this is called a dot product. So you're interested in the value of the magnetic field along the direction of the loop itself. That's what it means, along the direction of the loop itself. All right, so if the magnetic field perfectly lined up with the loop, obviously the angle is going to be 0. And if there's some kind of an angle in between, then it's not going to be 0. So the contribution of the magnetic field is going to diminish if it's not 100% along the direction of the loop. That's what it means. If they are perfectly lined up, the loop and the magnetic field, if they are lined up 100% because it's a circulating loop, and the magnetic field is also circulating, obviously I can express this dot product in terms of a scalar expression because the angle is going to be 0. And then ds is going to represent the circumference, 2 pi r, lowercase r. Do a back substitution, and then solve for b. And then once again, we recover the same expression that we had in the beginning of the lecture. All right, so the exact same mathematical expression for the strength of the magnetic field around the current line. That's it. Okay, so this one is so much faster. Okay, guys, couple of things that I have to mention. Problems that you guys are getting on the test are sophisticated. They're sophisticated. They're not so sophisticated that you have to kind of use the Biot-Savart's law, but they're sophisticated enough. You have to show the transitions, how you go from a vector expression to a scalar expression. And you have to keep it really clean. You cannot use algebra, right? When it is called for you to use calculus, you have to use calculus. And in this case, instead of using calculus, I said, okay, I just told you that this is the circumference. If you tell me that this is the circumference, if you can justify that expression, I will let you get away with an expression like this. Okay, you cannot turn everything into algebra, which it's not at this level. You guys are taking university physics, not college physics. You cannot oversimplify the mathematics without any justification. I'm able to get away with this sort of stuff at this level because it's physics. I'm putting the emphasis on physics. At the same time, calculus is kind of required so that you can follow the derivations. But in reality, when you guys do this at the next level, your instructors, your professors will not let you do it this way either. All right, you can't just make a one statement and move on to this expression. You actually have to show work. Okay, at that point, you will start using calculus regardless. You will be focusing on the angles, this and that. So they're not going to let you take shortcuts like that. All right, so just a warning. I'm noticing that you guys are trying to take shortcuts. Don't do that. Every time you guys do that, regardless of what the answer is, you lose points. Okay, so you get graded on your solution. The solution is a process of solving a problem, not necessarily the answers. Most of the time, I don't even look at the numbers. I check to see how you guys are solving your problem, whether or not you're able to explain what's going on, and whether or not you really get the concept. Because from the way you guys set it up, immediately I know whether you understand the concept or not. So, and then you have to kind of justify and explain the way I'm justifying and explaining stuff. All right, so it's still physics, whether you express it mathematically or in English, it's still a conceptual process. All right, so the next one is solenoid. Okay, these derivations are known as physics, obviously. How you come up with these formulas is where the emphasis is usually. All right, so if it's a solenoid, this is the expression that we have. All right, so the question is, how'd you come up with that? Where'd you get that from? What's the idea behind it? All right, once again, it's a derivation. It's a straightforward derivation. The nice thing about this derivation is Ampere's law is clean. You can apply it. Every time I'm using an Ampere's law, obviously I want you to pay attention because more than likely you'll have a question similar to one of these. Okay, now I'm interested in the strength of the magnetic field within. All right, so once again, we will make the assumption that this is an infinitely long solenoid, which means that there's not going to be any magnetic field outside. All the magnetic field is going to be within. And then notice that the magnetic field lines are parallel to each other. So what that means is the strength of the magnetic field within is going to be constant. So assumption after assumption after assumption. So accuracy of our solution is going to be just as good as the accuracy of our assumptions in this case. All right, so how do we do? Evidently, I just skipped that one. All right, so problem number 3 from the handout. All right, so this is one of the problems that I want you to focus on because not only it's a standard problem, also it's an interesting problem. All right, it's a potential test problem usually. Okay, so we know that the strength of the magnetic field outside is going to vary depending upon the radial distance from the wire, right? So the question becomes, how about the strength of the magnetic field within the wire? So what happens to the strength of the magnetic field inside? All right, so is it constant or does it vary? So that's the question that we will try to address. All right, so problem number 3, this is just the setup. You get a bunch of numbers. So it's a long straight wire. It's got a radius. It's got to be expressed in terms of millimeters. And this is the amount of current which is carrying. So what's the strength of the magnetic field right at the surface of the wire? And then the next question is, what is the strength of the magnetic field within? Remember, guys, this is the radius, which is 1.5 millimeters. And now we're looking at the strength of the magnetic field within, which is 1.2 millimeters away from the center. So we know that the outside of the wire is going to diminish radially as the square of the, it's going to diminish radially inversely, not square of the distance. It's something like that. It's going to vary. So what is the strength of the magnetic field within? All right, so how do you do a problem like this? All right, the best thing to do is just apply the Ampere's law. That's what we will do. All right, so this is being done during a live lecture. All right, so we're probably not going to have any numbers for this one. All right, so the first question is, what is the strength of the magnetic field right at the surface of the wire? So here's the radius of the wire. Okay, so we're looking for a mathematical expression for it. The best thing to do is obviously use the Ampere's law. Magnetic field, so here's my Amperian loop. So the direction of the magnetic field is along the same direction as the loop. So this vector expression can become a scalar expression right at that point. All right, so here's the scalar expression. Angle between the current as well as the loop, direction of the loop, this is going to be 0, so cosine of 0 is going to be 1. All right, so this expression is going to go to 1. All of a sudden, the left-hand side can be expressed in terms of a scalar product between D and S. All right, strength of the magnetic field at this radial distance is going to be constant, so I can actually factor that out. I'm not sure if I will do that. Yeah, I will. All right, so once again, for the reasons that I expressed before, ds, if it's a perfect circle, this will be the circumference at that point. Okay, so this r should be the capital R that we're looking at. I decided that the capital R also is my position vector in this case, so it's going to be the same as lowercase r. So they are the same in essence. Okay, fine. So this would be the strength of the magnetic field right at the surface of the wire. Okay, so this was good. It worked out. Okay, so the question becomes, so as you start to, if you're outside of the wires, strength of the magnetic field is going to radially diminish, so we kind of know that. So the question is, what if you're inside the wire? All right, so what happens to the strength of the magnetic field at this lowercase r, so within the wire itself? Okay, once again, we will get to use the Ampere's law. So this is our Amperian loop. Okay, guys, it's not supposed to be jaggedy like this. It's just, sometimes that's what happens when I'm using my iPad. All right, so Amperian loop is perfectly lined up with the direction of the circulating magnetic field. So once again, we can use a scalar expression for that one. Okay, so I prime is going to represent the current within the Amperian loop. So this is the net current within the Amperian loop. All right, so that is the net current within the Amperian loop. Okay. Just want to make sure. Okay, cool. This is the second part of it. Suspense. All right, so that's the Amperian loop. All right, so this is inside, outside. We did that. All right, so this is the net current inside the Amperian loop. All right, once again, B at this radial distance is constant, so I'm going to pull it out of the integral. Okay, so ds, once again, the circumference. In this case, the circumference is going to have the radius lowercase r, so it's going to be 2 pi r. Do a back substitution, and then solve for b. Are we done with this one? Okay, once again, if you're doing it blindly, just using the math, you think that you're getting somewhere. Again, useful, you're not getting anywhere. You just come up with a mathematical expression, and according to this expression, the strength of the magnetic field inside the wire is going to diminish inversely relative to the center of the wire, and then it depends on the amount of current within the Amperian loop. We know something about the amount of current inside the wire, but we don't know anything about the amount of current inside the Amperian loop until we know what this I prime is. In terms of the total current, we're not done yet. So which means that we have to come up with an expression for I prime. All right, so which means that we have to express the amount of current inside the loop in terms of the amount of current inside the wire. We know the amount of current inside the wire, but we don't know the amount of current inside the loop. So how do we do that? Look, guys, the amount of current inside the loop is not the same as the amount of current inside the wire. They're not the same. The amount of current inside the loop is going to be proportional to the amount of current inside the wire. But by how much? How much of this current is inside the loop becomes the question. And the only way we can solve that problem is if this current inside the wire has a constant current density. All right, so which means that the current within the wire, the amount of current per area has to be constant. So which means that the current has to have a constant current density. So the current per area is known as current density. It has to be constant. If it is constant, then this is a solvable problem. If it's not constant, then we wasted a lot of time. Okay, we just play with math and then we waste a bunch of time. That's the extent of it. So J represents the current density. That's the amount of current per area within. If this is constant, then perfect. We can solve. If this is constant, the amount of current inside the wire, area of the wire, is going to be the same as the amount of current inside the area of the Amperian loop, and that's it. All right, so you know by definition the current, no, not the current, area of a circle is going to be pi r squared. All right, so this is the area of the wire. All right, capital R is going to represent the radius of the wire, in essence, and this is the area of the Amperian loop. So solve for I prime. Wow, okay, and then do a back substitution to the Amperian, which happens to be this. And then let's check to see if we have any cancellations. All right, so now this is the total current inside the wire. Lowercase r represent the radius of the Amperian loop. Okay, so we got a square, and you got r, so there's going to be a cancellation there. Capital R is the length of the wire. All right, everything that you're looking at is constant here, so which tells you that the magnetic field within the wire is going to change linearly with the radial distance. All right, so as you start to move towards the edge of the wire within, the magnetic field is going to get stronger and stronger all the way to the perimeter. All right, that's what it means. And once you're outside, it's going to diminish as the square of it's going to diminish inversely, not as the square, but it's going to diminish inversely. That's it. Okay, that's the square. I don't know why I keep thinking square because of Newton. Okay, so that's it. Notice that you can actually analyze what's going on. So the magnitude of the magnetic field within is going to increase radially all the way up to the edge. And then once you're outside, the value of the magnetic field is going to diminish radially as it's diminished radially. That's what it means. So if there's going to be an inverse relationship, all the way to the edge, strength is going to increase. Once you're outside, it's going to vanish with the distance. All right, so solenoid is the one that we're dealing with. So my slides are kind of slightly out of order. Okay, so this is another application of the Ampere's law. Once again, let me just go over the basic assumptions. It's an infinitely long solenoid. All the magnetic field is trapped within. Strength of the magnetic field within is constant, so it's a uniform magnetic field. So with those assumptions in mind, these are the oversimplifications, oversimplifying assumptions in mind. What would be the strength of the magnetic field within a solenoid? All right, so the easiest thing to do is just set up your Amperian loop. This is going to be our loop. Boom, boom, boom. It's just going to run just like that. And then according to the Ampere's law, all right, so the strength of the magnetic field, circulating magnetic field, along the direction of the loop is going to depend on the net current within. So we will have to look at the net current within. So this is going to contribute to current. So is this one, so is this one, so is this one. So you got a bunch of contributing factors to current. All right, so according to the Ampere's law, once again, what's important is the direction, the component of the magnetic field, which is along the direction of the loop, is going to be affected by the net current within. All right, so on the left-hand side of this equation, I'm just going to do an oversimplification first, and then I'll take you through the derivation one more time. All right, so the equation looks like this. All right, so I'm just going to loop in the counterclockwise direction. I'm going to take a look at the magnetic field and along the direction of the loop. All right, so this is a dot product at this point. All right, so what do we have? Loop is moving in this direction here. This is our ds. The magnetic field is all in the same direction. They're in the same direction. So what is the angle in between? It's going to be, angle is 0. The cosine of 0 is going to be 1. And all of a sudden, this becomes one of the contributing factors. All right, so what do we have? This is the contributing factor. So I looked at only this portion of the loop. This is your ds. And then what happens? The loop is going in this direction. Now my loop turned up. All right, so this is the direction of the loop. The magnetic field is still pointing in this direction. Now, what is the angle now? It's going to be 90 degrees. Cosine of 90 is going to be 0, so this is not going to have a contribution. Now my loop is moving in the opposite direction. The magnetic field is from left to right. Yeah, but that's the magnetic field inside. There's no magnetic field outside. Well, if there's no magnetic field outside, this doesn't have a contribution, so this is no good. This is no good. Now my magnetic field is still pointing from left to right, and the loop is still 90 degrees to it. So direction of the loop and the direction of the magnetic field, 90 degrees, cosine of 90 is going to be 0, so this doesn't have a contribution. So notice that only contribution of the magnetic field along the direction of the loop happens inside the solenoid. And this ds happens to be the length that you're going to be looking at. All right, so this ds is going to be the length between A and B. All of a sudden, this expression that you're looking at becomes D times L. And what do you have on the right side of the equation? So you have mu naught times the net current within the loop. All right, notice that nothing is memorized. Okay, this is how you do the analysis. Okay, everything is understanding based. This is what makes physics so much more difficult than any other discipline. Everything is driven by the quality of the understanding that you have. Okay, now that I did this little explanation, now you guys are ready for the derivation. Now we can just jump into the derivation at this point. All right, so against that background, I gotta get rid of this. All right, so in essence, outside there's no magnetic field. Once again, it's an infinitely long solenoid. Assumption is that within, strength of the magnetic field is constant. All right, so the strength of the magnetic field along the direction of the loop is going to be determined by the net current within. So that's what Ampere came up with. Now the net current within, it's not just one single current element. You got 1, 2, 3, God knows how many. It depends on the number of turns that you have, right? Okay, so you got the number of turns. So each and every single turn is going to have the same amount of current. So N represents the number of turns within the Amperean loop that you're looking at. So which means that we will have to do a back substitution to that. Okay, the left-hand side, I discussed that. The strength of the magnetic field along the direction of the loop is going to be the inside component, which is this portion, which is going to be the length between A and B that you're looking at. So we end up getting, for this expression, the only surviving term is going to be L. All right, so this is the only component along the direction of the magnetic field. The only component parallel to the magnetic field. That's what it means. And now we're ready to solve for B. Dividing both sides by L, that's the length within the Amperean loop. Number of turns per length is going to be lowercase n. This is like the length density. I'm just making things up right now. So number of turns per unit length. Then we end up coming up with the expression that we'll get to use for the solenoid. This becomes the expression. Okay, something is deceptive about this. What's deceptive about it is the oversimplifications that we made. We came up with a lot of simplifying. Okay, so we made a bunch of underlying oversimplifying assumptions. You know, it's on the reality of it is no one has an infinitely long solenoid. There's no such thing, obviously. All right. What that means is the strength of the magnetic field within cannot be constant. Okay, so despite the fact that we came up with that expression, only at the center, and notice that you have to be away from the edges quite a bit. Certain region within a certain region, I think you can come up with a pretty good approximation of constant magnetic field. Right. So every time we're dealing with the concept of magnetic field within a solenoid being constant, just remember we're always talking about the center towards the middle. Okay, so it's a good approximation. It's almost like ignoring air friction. Everything follows at the same rate. Once again, you will have to do some oversimplifying assumptions in order to solve these problems. All right, so the next one that we will be interested in is the solenoid being turned into a donut shape. All right, so take a solenoid and then just turn it into a circle, make it into a donut, and you call it a toroid under the circumstances. So donut-shaped solenoid becomes a toroid. Now the question becomes, what happens to the strength of the magnetic field within? All right, and once again, these have engineering and physics applications quite a bit. All right, so the question is the strength of the magnetic field still constant? So the best thing to do is just draw out your Amperean loop, which is right at the center right here that you're looking at in green. So that's your Amperean loop. And then using the Amperean loop, just come up with a mathematical expression for the strength of the magnetic field inside the loop. All right, so this is inside, this is outside radius that we are looking at. All right, so once again, Ampere's law. All right, so this is going to represent the number of current elements within the loop that you're looking at. Okay, so what else do we have? Strength of the magnetic field at this radial distance is going to be constant at that radial distance. All right, ds represents the circumference of the Amperean loop. And then we came up with a mathematical expression for B. All right, so this is number of turns per unit length or through the total length of the circle, which happens to be a circumference. So what that means is strength of the magnetic field is going to have a radial dependence. All right, so the outer edge of the toroid, the magnetic field in the outer edge is not going to be as strong as within the inner edge. That's what it means. So further away you get from the center of a toroid, the weaker the magnetic field is going to become. All right, so what happens inside the solenoid is not the same as what happens inside the toroid. Inside the solenoid, assumption as well as the math, is that the strength of the magnetic field is going to remain constant at the center, but inside a toroid, it's got an inverse radial dependence. All right, so these are the formulas that you need to know, obviously. All right, so the first formula is going to give the strength of the magnetic field at a radial distance from a straight wire. The second formula is going to give you the strength of the magnetic field at the center of a circular loop. Okay, so this is the one that we will focus on next. We talked about a solenoid, and lastly, we talked about a toroid. In the solenoid, the strength of the magnetic field is constant. Inside a toroid, it's not. Inside a toroid, it's going to have a radial dependence. Yeah, let me just check to see what we got here. Okay. All right, so inside a toroid, it's going to have a radial dependence. Okay, this is good. Okay, so this is the last one of the derivations that we kind of have to go through. What if you have a circular loop? All right, this is one of those weird things. You can apply the Ampere's law to this one. It's not going to work. All right, so for a setup like this, we'll have to use the Ampere's law. That's what we have to do. All right, so the circular loop like that is going to act like a magnet, so you can turn this into an electromagnet. Okay, something that we discussed before, which means that the magnetic field lines will just wrap around in this fashion. All right, so the question becomes, be interested in the strength of the magnetic field inside, right at the center. So how would we compute the strength of the magnetic field inside a loop like that? And then maybe express it as a magnetic dipole, whatever that means. Something that we discussed before. All right, so you guys, you'll get used to doing these problems time and time again. Like I said, next level up, that's what you guys are going to be doing. A lot of mathematical applications to these concepts. So hopefully you guys are getting the physics right now. So what is the strength of the magnetic field inside the loop, at the center of the loop, in this direction? Guys, the magnetic field, notice that it's just looping around. So we are trying to come up with a generalized expression for the strength of the magnetic field pointing in this direction. That's what we want. All right, so this represents a circular loop. Believe it or not, let me just express it using this one. All right, so the current is coming out of the page, it's going into the page. So this is a loop of wire. So it's a two-dimensional representation of a three-dimensional loop. I'd be interested in the strength of the magnetic field at this point. You know, the magnetic field is going to be looping around in this fashion, right at this, it's just going to be looping around the wire. All right, I ran out of room there. All right, so this is, my circle is not perfect. All right, so this represents the radius of that circle. Notice the magnetic field is just looping around in that fashion. All right, so I'm not going to even use this. All right, so it's pointing in this direction. So it's going to have two components. One component is going to be parallel to the z-axis. So the other one is going to be perpendicular to the z-axis. So this is the component that I'm interested in. What is the value of the magnetic field, which is going to be perpendicular to the area of the loop, in essence? All right, so that's what we're after right now. All right, so instead of Ampere's law, I always say it doesn't work. Not that I've tried it. I had a student try it, couldn't figure it out. So instead, we traditionally use the Biot-Savart's law for that purpose. Okay, so a couple of things to focus on. All right, so before I do that, let me just check to see what it is that we have that we can use. Okay, in terms of the setup, okay, so we got alpha here. So alpha in this case is an angle, okay, when you set it up. All right, so this is the angle between, if you make a triangle like that, so this is the base of the triangle, this is the height of the triangle. So this is the angle between the base and the hypotenuse that we're looking at, and that happens to be this angle. Okay, okay, so when you're looking at a book like that, despite the fact that I'm putting the emphasis here, in reality, if I'm doing everything from scratch, I know how to get, by using the Biot-Savart's law, I can figure out the differential value of the magnetic field right at this point, right? And then I'm interested in the value, which is going to be perpendicular to the surface. So I would be interested in this angle. So the only thing you need to know is, if you know this, you can figure out this one. Okay, so the cosine of this value is going to be this component that you're interested in. And you can figure this out only if you know something about alpha. And obviously, there's no way you can figure out alpha from this setup. But there are measurables over here. So you got the position vector located here. You would know the radius of the circle that you're looking at, and you know the height relative to that, and all of a sudden you need to know that this alpha is the same as this alpha from basic geometry. Okay, so that's what we will get to explore. So this alpha, you need this alpha, and you will get this alpha by looking at the triangle that you have down below. All right, so we're still looking for the strength of the magnetic field, which is going to be perpendicular to the area, right in the middle and the perpendicular. to the area of the loop. All right, so Biot-Savart's law. All right, so we got the formula for that one. So ds obviously is the circle that you're looking at. All right, so differential elements in this case is coming out of the page. All right, right here the current is coming out of the page. R is going to be 90 degrees to the direction of the current that we're looking at. So I'll turn this into a vector expression just briefly. And this theta is the angle between the direction of the current, or current element, and it's also going to be related to the direction of the position vector. So the current is coming out of the page, and notice that this is the position vector moving in this direction. Look, guys, this is going to be 90 degrees to the direction of the current element. So which means that sine of 90 is going to be 1. So all of a sudden, we end up getting a simplified expression for the strength of the magnetic field. Now we come up with an expression for this one. Now I'm interested in the component of this, which is parallel to the z-axis. So which means that it's going to be cosine of this angle, not theta. It should be alpha. Hopefully, I'm going to see that and make a correction. All right. I didn't see it there, but obviously mentally I'm still all together. So I make the correction right there. That's a correct expression. All right. So now we have to express this angle in terms of measurables. R, Z is something you can measure. This is the radius of the circle. So the cosine of this angle that you're looking at, so it's going to be adjacent over the hypotenuse. So it's going to be adjacent over the hypotenuse. So do a back substitution. All right, so what else do we have? All right, so R squared, R is going to be R cubed. This capital R is not going to change, so I can move this out if I wanted to. All right, so I'm just going to keep things as they are. All right, so what else? ds is going around like that. All right, so what's changing? Do I have any variables? All right. Everything seems to be a constant in this case. Capital R is going to be a constant, and check to see. I'm trying to figure out at this point how to do the integral. Trying to figure out what's changing. Only thing which is going to change, R can change, is a function of Z. All right. Okay, depending upon where you want to put your point, so R is going to change depending upon Z. So if my point is up here, Z is going to change, R is going to change. So, which means that I have to express R in terms of Z. And you know that this is your tiny little triangle here, right angle triangle. So which means that I can use the Pythagorean theorem and work it out. But if R is constant, then everything is fine. All right, so if you take R as a constant, then obviously, and that's what I'm doing right now. Guys, in real life problems, when you're taking this course over again at a higher level, more than likely they will move the point. It's going to be a variable point. All right, so which means that the S is going to be expressed in terms of R in essence. Here, this point is at a constant location. So I said, okay, so which means that I can turn this into a circumference, and then at that point I'm done. All right, so this is a simple version of a more complicated problem. All right, so I'm looking at right now, I see a bunch of cancellations. So pi's, and then you have 2 canceling out of this. All right, and then we have R, capital R and capital R, so it's going to give you a square. All right, so here's the strength of the magnetic field right at the center of a loop, a distance R, radial, this represents a position vector. R from it. Okay, so now we got to come up with a little bit better expression for that one because this R really complicates it. I'm looking for a simplified expression for it. All right, so I can express R in terms of Z and obviously also use capital R. Okay, so I'm going to use the Pythagorean theorem at that point. Do a back substitution. All right, so this is going to be this expression raised to the power of 3 halves. And okay, now if I'm interested in the strength of the magnetic field right at the center of the circle, I can make my Z 0. All right, now I'm interested in the strength of the magnetic field right at the center of the circle, so Z becomes 0. And obviously it's square, and then this 2 will cancel. This is going to be R cubed. This is R squared. All right, so you got your cancellations. And then this is exactly the same expression that we had in the beginning of the lecture. And just about the only way you can get this expression is by using the Biot-Savart's law. Okay, I'm going to take 3 more minutes and turn this expression into something else. Okay, so I'm going to express the strength of the magnetic field at the center of a loop, circle loop like this, circle loop of current, in terms of a magnetic dipole moment. All right, because this loop is going to act like a magnet. That's what it means. excuse me. So that's what I'm gonna do. So this becomes a case number 2. Do I want to do that? All right. What is this component of the magnetic field which is going to perpendicular to the area of the loop when Z is much larger than R? Okay, so so that's what we're interested in right now. Okay, so this Z is going to be much larger than the radius that you're looking at, capital R. So what would happen to the magnetic field at that point? Okay, so this is what I'm going to use the magnetic dipole moment expression, because this thing is going to act like a magnetic dipole. All right, so if Z is much bigger than R, like this is a million and this is 1. All right, so R is going to be so small that we will just ignore it. All right, just ignore it. Just pretend that it's not there. Okay, I'm not going to even use anything else. I'm just going to look at it and say that's just too small. Let's just ignore that expression. When you ignore it, this is the expression that you come up with for this strength of the magnetic field at a certain height along the Z direction away from the loop itself. All right, so you got square, and then obviously you got the second power inside the denominator, so they will cancel. And then we have an interesting expression here. All right, so we got the current, we got R squared. So if I were to multiply this by pi and divide it by pi, this R squared can become area. All right, so if I multiply top and bottom by pi, then all of a sudden I'm going to have an expression in the numerator that's going to be the area of this loop. In the denominator, I'm going to have an extra constant, which is fine. It's not a big deal. The combination of the current and the area of the loop for that current is known as the magnetic dipole moment, something that we discussed before. So that expression that you're looking at is going to tell you how much this loop is going to act like a magnet. All right, so this becomes a magnetic dipole moment. And that's for the magnetic dipole moment. That's the reason why we're always interested in the strength of the magnetic field right at the center. So which means that this current loop is going to act like a magnet. How much it's going to act like a magnet is given by this formulation. And that's it. All right, so this is the strength of the magnetic field expressed in terms of how much the loop acts like a magnet. Dipole moment. All right, so this stuff is long. Okay, guys, there's no test this week, obviously, so I just finished up the lecture. Everything is going to go. We got a few more minutes. Okay, so remember, every single atom is a magnetic dipole moment in that sense. All right, so you got an electron moving about the nucleus. It creates a small current loop. The current generates a magnetic field, looping magnetic field. And the value of the magnetic field in the metal is going to be associated with the magnetic dipole moment, which means that every single atom acts like a microscopic magnet.
The circular loop of electric current also creates a magnetic field of this form. And so does every proton, every neutron, and every electron in the universe.
All right, so every single atom can act like, hey, get down. Every single atom acts like an atomic magnet, provided that they have a magnetic dipole moment. If they have a magnetic dipole moment, they will act like a microscopic magnet. Okay. And they're going to be facing a random direction, so that's the reason why not everything is magnetized. But if you can get all these atoms pointing in the same direction, then the structure becomes magnetized. So which means that the dipole moments will get lined up along the direction of the external magnetic field.
A magnet experiences equal and opposite forces at its poles, so that it tends to line up with the field. In other words, the field exerts a torque that tends to make the North Pole point in the direction of the field. In fact, that's how the direction of the field is defined.
All right, so within iron, obviously you got these domains within which the atoms are pointing in the same direction or facing in the same direction, which means that their magnetic dipole moments are lined up in the same direction. So if you can get all the atoms facing the same direction, if you can get the dipole moments of every single atom facing the same direction, then it becomes magnetized. You could do so by using a magnet. Okay, so we discussed this